You may know that the photoelectric effect explains that light can be quantized packets, called photons. So if that's true, why wouldn't we see light as individual particles? Well, today we will explore this through some maths. So let's imagine that we are looking at an 100-watt light source, which is comparable to that of a candle, from 100 meters away with a wavelength of 550 nanometers, which is in the visible spectrum. How many photons would hit our retina every second? Right, so first, we know that power is equal to energy divided by time. We also know that the energy of a photon is equal to hf, which is Planck's constant times its frequency. Okay, so this is for a single photon. If we want multiple photons, then we want the energy to be times by the number of photons there are. So this means that we get the energy is equal to the number of photons times h, with Planck's constant, times the frequency. So we know this. So what we can do is we can substitute E into the power equation. So energy is subbed into the power equation. So we can get power is equal to the number of photons times Planck's constant times frequency divided by time. Okay, well, another equation that we know is that the wave speed is equal to the frequency times the wavelength. So we have a common thing here. We have frequency here and we have frequency here. So we can do frequency is equal to the wave speed divided by the wavelength. So now we can sub f in. So this is going to be the number of photons times Planck's constant times frequency times c over lambda divided by time. And we can simplify that to be the number of photons times Planck's constant times frequency times the speed of light. Sorry, I should get rid of that f. There you go, because we subbed f and we replaced it with these. So nhc over t times wavelength. So now we have this equation linking lots of different things, but we actually wanted to find how many photons hit our retina every second. So we want to find this value. We want to find n, the number of photons. So what we're going to do is I'll rewrite it here. Power is equal to nhc over t lambda. So if we want to rearrange to get n, then we times over by t and lambda. So p t lambda is equal to nhc. Now if we just want to get n on its own, then we move the hc and divide it across. So then we get n is equal to the power times the time times the wavelength divided by Planck's constant times the wave speed. So now we have this equation, we can sub in our values. So we said that the power was 100 watts. We said the time, because we want per second, it's just going to be 1 per 1 second. The wavelength we said was 550 nanometers. Now what that is 550 times 10 to the minus 9 meters, because nanometers is to the minus 9 meters. Okay, and then times Planck's constant, which is 6.63 times 10 to the minus 34 times by the wave speed. Well, we're working with light here, and we know the speed of light is going to be, well, in a vacuum, is 3 times 10 to the 8. And if you put that in your calculator, you're going to come out with 2.77 times 10 to the 20 photons per second. Photons per second. Right, so now we've got the total amount of photons that the source emits. Now we want to find the amount that actually hits our retina. So we have this 100-watt source, and what we can imagine is that we have this 100-watt source like this, and there's, I'll only be able to draw a 2D, but it would be 3D. There's a sphere round this light source, and we're standing right on this edge here. So the distance between us is 100 meters. And that is the amount of area that the light has spread out when it reaches us. So we can use this in a type of ratio. So we're gonna do the the area total. We're gonna have the area total, and we're gonna have the area of the eye, and then we can have the photons, the total amount of photons, and we can have the amount of photons that hit the eye. So these are the four things which we can create a ratio out of. So let's first find the total area that the light has been able to spread out when it's reached us. So we're finding surface area. So the surface area of a sphere is 4 pi r squared, which comes out to be, r would be 100, so that would be 10,000 times 4, so that's 40,000 pi. That's in meters squared. So that's the total area. Next we have the area of the eye. So we're going to say, well, roughly the area of the eye is 10 millimeters squared, which is equal to 1 centimeter squared, which is equal to 0.01 of a meter. Okay, so we've got these two. We know that the total amount of photons, because we worked out in the last question, so the total amount of photons we worked out to be 2.77 times 10 to the 20 per second, okay, because we're all working this out per second. So now we want to form the ratio, so we're going to say that the total area divided by the area of the eye is equal to the total amount of photons divided by the photons that hit the eye. Because we can think as the photons spreading out, and as you get further away, then the photons become more spread out, so there's less of them per area. So we're taking up a small proportion of that surface area around the circle. Okay, so our eye is a proportion of that total area, and therefore it's a proportion of the amount of photons. So we want to find out the total photons that hit our eye. We want to find this value. So we can rearrange. So we want to get this onto the other side. So we can say that, I'll do it the long way, the total area times by the total amount of photons is equal to the photons in total times by the area of the eye. Now we still want to get P, so the photons that hit the eye is the total amount of photons times the area of the eye divided by total area. Okay, so now we've got that, we've got all of our numbers, so we can plug them in. So it's going to be the total amount of photons, which worked out to be 2.77 times 10 to the 20 per second, times by the area of the eye, which was 0.01 of a meter, divided by the total area, which we said was 40,000 pi, and then we want to put that in our calculator and see what it says. So, right, and that comes out to be 2.2 times 10 to the 13 photons per second. So we found this output amount of photons, and then we used that in this proportion, so this proportion of the total area that our eye occupies, and we use this and that ratio to find the amount of photons that hit our retina every second. Right, so now that we've found the amount of photons that reach the eye every second, our brain doesn't process the image every second. It actually processes the image 30 times per second. Okay, so think of it as it takes a reading of the amount of photons every second. That's a simplified view of it. So for every refresh of our eye, we don't have 2.2 times 10 to the 13 photons. We actually have to divide that by 30, because that's the amount we see per second, but our brain refreshes it every 30 times per second. So divide that by 30 and we'll get the amount of photons that we get per refresh. So 2.2 times 10 to the 13 divided by 30 is going to give you 7.3 times 10 to the 11 photons. So that's, if you think about it being 10 to the 11, so 10 to the 9 is going to be billions, and times 10 to the 12 is going to be trillions. So being 10 to the 11, that's 730 billion photons, which hit our eye every time our brain takes a reading from our eyes. So that's quite amazing, 730 billion photons. I mean, that's why you don't see your packets of light. But we can go even further than this, and we can work out how far away, so how far away, if we say this was the light source, you would have to be so that your eye would literally see one photon. Because the further you stand away from the light source, the more it spreads out. So the same amount of photons that this light source is giving, that's fixed. But those photons are spread over a larger area, which means that the proportion of our eye also stays the same. So that proportion becomes larger, and what we want to find out is at what distance here, at what distance d, our proportion means that we would see one photon, and that's what we're going to work out. Right, so to find this distance, we want to come back to this ratio. So we have the ratio of the total area divided by the area of the eye is equal to the photons, the total amount of photons divided by photons that reach the eye. So we got to figure out what we want to know. Well, the distance comes from the total area, so this is what we want to find. We can use that total area to find the distance. We want the photons that reach the eye, we're going to set that to 1. So we can find that area where the photons that hit our eye is only going to be 1. And the total amount of photons and the area of the eye will stay constant. So we want to rearrange this, so we're going to just times over by the area of the eye, so area total is equal to the total amount of photons times by the area of the eye divided by the photons that reach the eye. Right, so now we've got this, we can plug in our numbers. However, what we need to keep in mind is that now we're looking at these amount of photons 30 times every second. So we're not having one photon reach our eye every second. Because our brain refreshes every 30 times a second, we're having to basically divide this by 30. So rather than being 2.77 times 10 to the 20, because that's how many reach our eye every second, okay, so many photons that reach our eye every second, we want to divide that by 30. So if we do 2.77 times 10 to the 20 and we divide that by 30, then we get 9.23 times 10 to the 18 photons per, well, it would be 2 milliseconds, wouldn't it? Because 60 milliseconds divided by 30 milliseconds is 2 milliseconds. But that's how many photons hit our eye every 30 times per second. Right, so now we got that. That's going to be the amount of, that's going to be the photons that, that's going to be our total photons, where it gets a bit confusing. That's going to come in as our total photons, because that's the amount of photons there every 30 seconds. So, right, now what we want to do is plug these numbers in. So 9.23 times 10 to the 18, which is the total amount of photons every 30th of a second, times by the area of the eye. Now the area of the eye stays the same, and we said it was 0.01 of a meter. You originally said it was 10 millimeters, which we just converted. And so now we have the photons that hit the eye. Well, we know that wants to be 1, doesn't it? Because we want to know the distance where one photon hits the eye. So if we do that, then we'll do 9.23 times 10 to the 18 in brackets times by 0.01 divided by 1 gives us 9.23 times 10 to the 16. And that's going to be the total area, so it's going to be meters squared. Okay, so now that we've got this is our total area that it's spread out in, but we want to find the distance here. So we want to find the distance. So how do we find that? Well, we know it's a circle, and we know the equation of surface area for a sphere, sorry, it's a sphere, not a circle, is 4 pi r squared. We know 4 pi r squared is equal to 9.23 times 10 to the 16. So now we can rearrange. So what we want to do is divide by 4 pi. So if we do 9.23 times 10 to the 16 divided by 4 pi, then that gives us that r squared is equal to 7.35 times 10 to the 15 is equal to r squared, and then we're going to square root that, and we get r is equal to 8.57 times 10 to the 7 meters. So we can check that by plugging it back in. So if we do, let's try that. Let's do 4 pi times 8.57 times 10 to the 7 squared, and that gives us 9.23 times 10 to the 16. So that's the amount of meters. So let's think about this. So let's put it in a good measurement. So we know kilometers is times 10 to the 3. So that would be 8.57, times 10 to the 4 kilometers, which would be, if we go here, 1, 2, 3, 4, so 8, 5, 7, put 2 zeros on because we had the point there, we go 1, 2, 3, 4 kilometers. So that's 85,700 kilometers away. That's a long way, isn't it? Right guys, and that's why we don't see light as quantized packets of energy is, well, really because if we look back up there, 730 billion photons reach our eye every time our brain refreshes. So that's why it's a clear picture. That was a lot of calculations, so if anyone picks up on any mistakes or anything, then feel free to do so, or if anyone knows the exact amount of kilometers that this would actually be in real life, as I made quite a few simplifications, that'd be great if you could put it in the comments. But yeah, hope this was interesting, and see you later.